talk about Chapter 1, Building a Solid Foundation. I want to first start out by looking at the learning objectives for Chapter 1. We can see here that there's a list of these at the beginning of each chapter, and we can see that there are these section numbers. There's Section 1, 1.1, and 1.2, and so forth. And we can see that we can look at these to determine what we're supposed to be getting out of each one of these sections. And it's always a good idea to look at these before you start each chapter to see what sorts of things you're supposed to be gleaning from each chapter. So you can see that Section 1.1 starts out by defining engineering, fluid mechanics, and learning, and so forth. We're going to, in this chapter, define what a fluid is. It's a liquid or a gas, describe the characteristics of liquid and gases, explain how different approaches for describing fluids, either macroscopic or microscopic, and talk about what the continuum assumption is. Define a fluid parcel. We're going to work with dimensions, both in terms of what they are, what determines a consistent set of units, and then how we use the grid method to convert units and cancel them. I also note that section 1.6 here is a little bit misplaced, but I think we'll return to this again in chapter 2, but we will go through a discussion of the ideal gas law in this chapter as well. This book also adheres to something called the Wales-Woods model for solving problems, and I'll just briefly mention this, but you should note that each example in the book follows this method, and it's a step-by-step approach for basically solving engineering problems, and you can use it if you want. It will probably help you get a lot of points on the homework in terms of organizing your work. And then finally, we're going to talk about dimensional homogeneity and pi groups, which we will use later on in the course. So defining fluid mechanics. These are pretty straightforward. We have mechanics is the field of science focused on the motion of material bodies. So the motion of objects is mechanics. Fluid mechanics then is the science that's applied to understanding energy, motion, deformation, and properties when the material is a fluid or a gas or in gas or liquid phase. A fluid is a substance whose molecules move freely past each other. And so we'll see here in a minute that it's really the intermolecular forces that keep a liquid together, or a fluid together. But these parcels are not bound to each other like they are in a solid. They're not in a solid lattice. A fluid is also a substance that will continuously deform under the action of what are called shear stresses, and we will be looking quite a bit at shear stress in this course. So let's take some time to look at types of matter, and to distinguish a solid, liquid, and a gas. And so if we start here with the column under solids, we can see that solids are materials that hold their shape. They don't need a container. Molecules have low mobility because they are bound in the structure by strong intermolecular forces. And you can see here in this lattice here that that this is really a these molecules are bound together so that they don't necessarily move. A good example of this that I gave in class was a table. A table is a structure. It's when you push on it or move it, it doesn't readily deform. The density is often high in a solid. This is the density of steel. For instance, maybe the table legs are made out of steel. Or pieces of your chair at school might be made of steel, and the density is 7,700 kilograms per meter cubed, whereas the density of water is almost 8 times less than that. So steel is quite dense, solids are quite dense. The molecular spacing is small. because the molecules are close together, and we can even see that here in this picture, that there's this cartoon basically of a solid, and the molecules kind of describes that. If you apply shear stress to a solid, it's going to produce deformation, and that is it will basically stretch, and if you applied a shear stress at the top of the solid, it would basically stretch this top part relative to the bottom, and it would deform the solid, but it would not flow. If you then let the shear stress go, the solid might pop back to its original location. If you applied enough shear stress, you would break these bonds, and you would break the solid up. Under normal stress, that is stress coming, say, from the bottom or from the top, under that you're going to produce deformation that may cause a volume change. So in other words, if you squeeze this thing hard, it may in fact compress, or if you somehow pull it apart, you might be able to expand it. Viscosity doesn't apply to this because viscosity is really frictional, a way of describing friction within a fluid. And since this is a solid, it doesn't apply. Compressibility, for a solid, it's difficult to compress, and because the molecules are already pretty close together. Now, going to the next column in liquids, we can see that a liquid is going to take the shape of the container, and it'll stay in the container due to the force of gravity. And molecules move around freely, even though they're bound, still bound by strong intermolecular forces. The forces are just not quite so strong, quite honestly, because the liquid usually is at a higher, you would have to cool it down for it to go into a lattice form. A good example of this is water turning to ice as you cool it. If you cool water down far enough and remove that thermal energy, it will enter the solid phase. It's of medium density. Water is about 1,000 kilograms per meter cubed. Let me just take a second to say what that number means. A meter cubed is about 3 feet by 3 feet by 3 feet, so this is kind of a big box. But 1,000 kilograms, that's quite a lot of weight. It's 2.2 pounds per kilogram. And so that water is going to be, that much water is going to be quite heavy. If you apply shear stress to a fluid, it's going to produce flow, and if you squeeze it, it's going to deform it, and it's going to be associated with a volume change. You will be able to compress this if you say press down on the top of this thing. It will in fact change the volume. And that can happen because there's already quite a lot of space between the molecules. It's difficult to compress still, not entirely impossible, but it's difficult. A gas, on the other hand, gases are going to, you can see that this container is now capped. There's a lid on it, and the gas will basically bounce around until it diffuses and fills the space in the container. The molecules move freely around with little interaction until they collide with each other. The density is very low. This is maybe 1,000 times or almost 1,000 times less than water. The density of air at sea level is only 1.2 kilograms per meter cubed. The molecular spacing is large, and again, it will produce flow if it's subjected to shear stress. Normal stress will deform it. A good example of this is a piston. If this lid went down, it would compress this gas and cause the gas to change volume. The viscosity is low, which we'll talk about later, and it's very easy to compress. So those are kind of a quick description of the matter, and of course the fluids are the liquids and the gases here. So if we look at idealizing this matter, section 1.3, we can see that there are various different ways to look at matter. One of them is a microscopic view, looking at the behavior of the individual atoms and molecules within a fluid. This is typically not something that we'd want to do in engineering because we don't want to keep track of every little molecule. Instead, we're interested in how the bulk material behaves and how it moves and flows. Some of the key concepts when we're looking at fluids are the continuum assumption and what a fluid particle is. So let's take a look at the continuum assumption. This is a key concept that we use in engineering. We normally assume that this holds and that we assume the volume under consideration is large enough that we do not have to deal with molecular effects. So if we look at this area right here, if we're looking between volumes of sizes V1 and V2, volume 2 is going to be bigger. So if this little sphere here, this little circle here represents V1, V2 would represent a larger circle. And what this is saying is underneath this area right here is that if you change the volume from V1 to V2, the density isn't changing. That means that as we increase the volume, the mass is changing at the same rate. And so the density is staying constant. If we make this thing smaller and smaller and smaller, pretty soon we're including or excluding individual molecules. And you can see that all of a sudden the density starts to vary wildly depending on how many of these molecules we are including in that small, almost infinitesimal volume. So in this case, we'd be containing less mass in that volume, and then when we change the volume, decrease the volume just a little bit, all of a sudden we added another molecule or so, or excluded one and whatever, and the density changes rapidly. So our volume has to be big enough so that it's constant. Now the interesting thing is that what if there was a density variation in this particular gas? Say it was higher density down here than up here. If we chose a very large volume, a very large sphere for our volume, the density actually might go up, or it could stay constant if there was no density gradient across this, or it might actually go down if we started off with our sphere up here in the low density fluid and then it started to include some more high density gas. So this area of the curve really represents density variations in the matter that we're considering, not necessarily an invalid continuum assumption. So moving on, one of the key concepts that we use in engineering is that of a fluid parcel. And a fluid parcel is a small quantity of fluid with a fixed identity. What do we mean by small? Small means smaller or shorter lengths than the lengths under consideration. So a good example of this might be an engineering, or not an engineering, but an irrigation channel that is maybe 10 meters across and 3 feet deep or 3 meters deep. And so if we might choose our fluid parcel to be a centimeter, 1 cubic centimeter out of all that water that's going through there. And so that fluid particle is very small compared to the dimensions of the channel being 3 feet by 10 feet. I'm sorry, 3 meters by 10 meters. What do we mean by fixed identity? Fixed identity means that the particle is always composed of the same matter. So if we track this little 1 centimeter cube within this irrigation channel, we can always follow that particle and it's never losing mass or gaining mass. It's always the same molecules of fluid or water hanging together with a fixed identity. Okay, so we've got these concepts for idealizing matter or fluid that we're going to apply all through this course, really. These are things that we're going to assume and use. Moving forward, we want to discuss dimensions and units. We're going to need this when we, throughout the whole course. And so it's amazing to me that The system of units, the System International system, the SI unit system, only has 7 primary dimensions. These are dimensions from which all other quantities can be derived. So we only have 7 dimensions from which everything else can be derived. And only a collection of these, only a subset of these are of interest to fluid dynamics. So we've got, obviously, length scales are going to be important, mass and time and temperature, and also perhaps the amount of matter are going to be important, but electrical current and basically the intensity of light are not going to be things that we're going to consider. So we only have maybe 4 or 5 of these dimensions, these primary dimensions, that we're going to be concerned with. Primarily length, mass, and time, temperature as well. And so looking down here, secondary dimensions are dimensions that that are made up of, that are basically combinations of the primary dimensions. So if we look at force, these square brackets denote that that we're going to be taking the units of this quantity force inside the brackets. So force can be broken out into mass times acceleration, as we know, and then we can proceed to write down what the primary dimensions are of these two quantities. So kilograms, or mass, is the dimension for mass, and then length per time squared is, or meters per second squared, or feet per second squared, is the acceleration. And so we can combine these and get the units basically of force being mass times length divided by time squared. And you can do this for any other sort of quantity. It could be energy, it could be viscosity, shear stress, and any other quantity that you're interested in. You should be able to basically decompose it into its primary units. Now, we know from past courses, statics and dynamics in particular, that we have 2 systems of units. We have this SI system, the metric system basically, and traditional system, the British system. And so we like to typically use the metric system if we can, but we also have to be cognizant of the fact that some engineering problems will use the traditional system, so we need to know both. But if at all possible, we want to stick with the metric system. So the book makes a recommendation for using units, and in particular, it says to use consistent units, that is, either this column or this column, because this eliminates extraneous unit conversions. You don't have to do a lot of unit conversions if you stick with one system or the other. Always use the metric system if at all possible and whenever possible. And then also be proficient with the traditional units, because you will also need to use those from time to time. And in this course, you will use both SI and traditional units.